You've seen this shape 1,000 times. On skylines, in news reports, in every stock photo of pollution ever taken. And most people are confident they know what it is. A nuclear reactor. It isn't. There is no fuel in here. No turbine. No reactor. In fact, and this is the part almost nobody knows, it's almost completely empty. A thin concrete shell, a shallow layer of plumbing near the bottom, and 100 meters of nothing. What comes out of the top isn't smoke. It's water vapor. Clean, warm, ordinary water vapor. So here's the real question. If it's just an empty shell, why does it need this exact curve? The answer is a story about two completely different branches of engineering arriving at the same shape, independently. And about what happened one November morning in Yorkshire, when engineers respected the shape, but not the reason behind it. Every thermal power plant on Earth, coal, gas, nuclear, it doesn't matter, runs on the same deal with physics. Heat goes in at high temperature, some of it becomes electricity, and the rest must be thrown away. That's not sloppy engineering. That's the second law of thermodynamics, and there is no appeal process. And the numbers are brutal. For every unit of electricity a typical plant generates, it has to reject roughly 1 to 2 units of heat. That waste heat leaves in cooling water. Warm water from the condenser is pumped to the tower and sprayed over a layer of packing called fill, where it trickles down as thin films and droplets. Air flows up through it. And here's the elegant part. Only about 1 or 2% of the water evaporates. But evaporation absorbs so much energy that this tiny fraction cools everything else. The plume you see is that 1%, condensing back into cloud. The deep mathematics of that heat and mass exchange is the Merkel equation. I've derived it from first principles in another video, link in the corner. But for today, only one fact matters. To cool that much water, the tower has to move an enormous mass of air. Thousands of tons per hour. With no fan. The tower is a machine for making air move using nothing but density. Inside the shell, warm humid air. Outside, cooler, drier air. The outside air is denser, so the atmosphere pushes down harder on the outside than the inside, and the light column gets squeezed upward. This is the stack effect. The driving pressure is beautifully simple. Delta P equals the density difference, times gravity, times the height of the column. Look at that last term. The draft is proportional to height. Double the tower, double the push. That is reason number one the tower is tall. Height literally is the engine. Now, the density difference. Warm air is lighter, obviously. But there's a second effect, and it's the opposite of what your intuition says. Humid air is lighter than dry air. I know. Humid air feels heavy. But a water molecule has a molar mass of just 18 grams per mole, against about 29 for dry air. Every water molecule that enters the mixture displaces a heavier one. Same temperature, same pressure, more moisture means less density. It's the ideal gas law, and the equation doesn't care about your intuition. So the tower gets a double push. The air leaving the fill is both warmer and wetter than the air outside. Both effects lighten the column. Both drive the draft. One subtlety. The draft also depends on how dense the ambient air is to begin with. Here in Kathmandu, at 1400 meters, atmospheric pressure is only about 87 kilopascals, so the same tower develops measurably less draft than at sea level. This is why real tower designs carry altitude corrections. Now watch the shape assemble itself from the physics. The base is wide, because that's where air enters. Maximum perimeter for the inlets, maximum area for the fill. The shell then contracts to a narrow throat. By continuity, the same mass of air through a smaller area means the flow accelerates. And above the throat, a gentle flare acts as a diffuser, easing the plume out and steadying it against outside wind. So thermodynamics wants tall, wide at the mouth, narrow at the waist, slightly flared at the top. But notice what it doesn't say. Nothing in the physics of draft demands a mathematically exact curve. For the exact shape, we need the second culprit. Take a straight line. Perfectly straight. A steel rod, a concrete edge, anything. Spin it around an axis, and you get exactly the shape you'd expect. A cylinder. No surprises. Now tilt that line. Don't bend it. It stays perfectly straight. Just lean it, and spin it again. The surface it traces out is curved. A waist in the middle, flaring at both ends. This is the hyperboloid. And every single curve you're looking at is made of straight lines. Nothing here was ever bent. And it's not one lucky line. 24 of them, evenly spaced, all leaning the same way, all perfectly straight, all lying exactly on the surface. Now here's the twist that makes engineers fall in love. There is a second family of straight lines hiding on the very same surface, leaning the other way. Two independent sets of straight lines, weaving one curved surface. Mathematicians call it doubly ruled. And in all of geometry, almost nothing else has this property. For a builder, this is gold. Straight formwork guides. Straight reinforcement paths. You can construct this exotic curve to millimeter precision using nothing but straight references. But the real payoff is deeper. Look at any point on this shell. It curves one way around the circumference, and the opposite way along its height. Curved in two opposing directions at once, like a saddle wrapped into a ring. Structurally, it means this. Push on the shell anywhere, and the whole surface pushes back. Load spread through the shell is pure tension and compression, membrane action, instead of bending. And a shell that never bends can be almost impossibly thin. These towers stand over 100 meters tall, with walls as thin as 15 to 20 centimeters. Proportionally, that is thinner than an eggshell. One last step. Real towers put the throat about 3/4 of the way up. Cut the same surface asymmetrically, long flare below, short lip above, and there it is. The shape you've seen 1,000 times, derived twice. But a shell this thin holds one uncomfortable truth. Its own weight is almost irrelevant. The load that rules its life, and its death, is wind.